So today and tomorrow I'll be discussing conformal field theory, still inspired by what we have seen and a bit related to ADS-CFT, but today there will not be too much ADS. So let me summarize what we have seen about ADS, but today we'll do more conformal field theory. And my impression is that you saw a little bit of two-dimensional conformal field theory because it was useful for string theory. You did not see too much of higher dimensional conformal field theory, is it true? Okay, so I will review a little bit. There will be some overlap to things you saw. So today it might be more like a summary of things you already know. So just yesterday we saw that ADS had at least three very useful incarnations. One as an hyperboloid, where we think of ADS roughly as a sphere, and then we have just rotations of this pseudosphere, so rotations of the y's that preserve its norm. And in that point, from that point of view, the isometries, the group that leaves ADS invariant, is a very natural group. It's just Lorentz transformations on a one-dimensional higher space-time. Okay? So if we have the isometry group of ADS5, our Lorentz transformations in R2, 4, so roughly R6. Okay? So we have Lorentz rotations in 6 dimensions, are the isometry group of ADS 5 dimensions. And that is also equal to the space of conformal transformations in one less dimension. Okay, so we have ADS, Lorentz in one more, or conformal in one less, and they are all equivalent. They are all isomorphic. Okay? So in different pictures, the boundary of ADS is seen differently. The boundary of ADS in the original Poincare coordinates corresponds to z equal to 0, which I remind you in the very first coordinates we introduced corresponds to r equal infinity, which means far away from the branes. In the cylinder picture, where we think of ADS as this global box where we have time and then a filled-in cylinder, then the boundary here is at rho going to infinity, where the metric approaches the metric of just a cylinder. So the boundary in that case would be a sphere times time, so we literally have a sphere and time. And in the hyperboloid, the asymptotic, the boundary of ADS are the light rays in one higher dimension. So light rays, which are 6-dimensional null vectors, which are projectively identified. And all this is equivalent to flat space up to eventually some wild rescaling. And indeed, for example, here we have flat space, here we have time times the cylinder, and the two are related by a wild transformation, as we saw. Now, a consequence of kinematics, basically, of identifying the generators and seeing how time evolves and how dilatations work, a consequence we derived, which is a very general dictionary, so I kept even D, I did not even specialize to n equals 4, because this is a kind of dictionary that in any ADS-CFT duality, this box will be true. In any ADS-CFT duality, if you have some ADS-D, and if you have strings moving in this global ADS-D, this will always be equal to the energy of whatever is your dual field theory, Yang-Mills theory, on R times the sphere. Simply because the times are the same. This same time here is the time in the boundary and the time in the box. So the energies are the same. This is not specific to ADS5 or anything. And the energy of Yang-Mills states on the sphere is also equal to the dimensions of Yang-Mills operator, the way they decay with power law, on flat space. And that's also generically true because this is true in any conformal field theory. In any conformal field theory, energies on the sphere are equal to dimensions in flat space. So this is the kind of dictionary that is hot to hold, but it's very non-trivial to check. It's very non-trivial to check because, say, these dimensions of operators in Yang-Mills, it's very easy to compute if the 't Hooft coupling is very small. When can you study easily energies of strings in ADS? You can study them if the string tension is very large, and then you just solve equations of motion for strings inside a box. So you get strings inside the box. So study some equations of motion, find the energy of those strings. This is true when the energy is very big, when lambda is very big, sorry. And operators in Yang-Mills, you just do two-point function, compute propagators, and then start putting loops on top of these propagators, and so on. And that's very easy to do when lambda is very small. Okay? And now the big challenge is how to crank up the number of loops here, or how to quantize the string here in order to meet in the middle and check the duality or derive the duality and so on. Okay? But right now, we can use these operators to predict what's the behavior of very quantum strings. Or we can use classical strings in EDS to guess what the behavior of the dimension should be as the coupling becomes very large. Okay? Good. So now I'd like to make some comments about conformal field theory. Okay. But first, is there any question? No. Okay. Okay. So in a CFT, we can think of it. It's a theory which has local dilatation. So one definition of a CFT is as follows. If I have some scalar, so it's not the general definition, but a consequence of being a CFT is the following. So if I have, say, so this would be a scalar primary operator of dimension delta 1. Okay, so I should explain what's a primary, right? I'm using the word primary. Is it familiar to everyone? Who does not know what a primary is? Who doesn't remember? Okay, very good. Someone at least. So, what's a primary? In a CFT, if we have some operator with dimension delta, that means that if I act with my dilatation operator on my operator, I get, say, my operator located at the origin, I get I delta times the operator. So this is how operators act on fields. Then we have, on the other hand, the algebra that tells me that K with D is equal to IK, and P, translations, with D is equal to minus IP. Okay? So all this algebra here, that is the algebra of the conformal group, there are many other relations, all this just follows from Lorentz. This is nothing but the Lorentz group in R2, D, right? So I just write the Lorentz transformations. J with J gives a bunch of J's. And then identify the operators like we saw yesterday, that some J's are dilatation, some J's are special conformal, and the particular case becomes some simple algebra, which is basically everything you can write. So here there is, okay, not everything, but this is what you get. And this has the following implication. This implies that if I have an operator, if O has dimension delta, it implies that P times O has dimension delta plus 1, and K times O has dimension delta minus 1. It's because it's basically the same thing as with the harmonic oscillators, right? You just act, if you just measure, because of the commutator giving plus I or minus I, you can show that the dimension increases or decreases when you act on the state. Okay? So this is very natural, because what am I doing here? This is nothing but derivatives of the operator, right? So if I take the derivative of an operator, I increase the dimension by 1, right? I add mass dimension 1, I put a derivative, I have mass dimension 2, right? So I'm increasing the dimension. And K is the inverse of P, it's the conjugate of P, and K therefore reduces the dimension by 1, okay? So now if I want the spectrum to be bounded, which means that I don't want to be able to act many, many times with K and go to minus infinity, I should have some operators that are killed by K. Remember that also this delta is the same as energies in the sphere. So if each state in the sphere should have some energy, and I should not be able to go to minus infinity if the theory is sensible, right? So delta bounded implies that an operator O can be of two sorts, can be a primary, which is an operator that's killed by special conformal transformations. So I start there. And then there are operators called descendants, which are of the form where the operator is of the form of acting with a bunch of translations on some primary. Okay? In other words, an operator, either it's a derivative of something else or not. If it's a derivative of something else, it's a descendant. If it's not, then it's a primary. And the operators, the spectrum of operators in a CFT is therefore, if you have the spectrum of dimensions, you have some delta of some primary, O1, and then a bunch of integer spacing. And then you might have another primary, say that could be here, and then another integer spacing again. And this would be delta of another primary, O2. Okay? So it's like a bunch of harmonic oscillators where we have some vacuum and then a tower of operators. Okay? Okay, so you see the most fundamental ones are the primaries, because if you know how to work with the primaries, the descendants are just derivatives of the primaries. So if you take, say, correlation function of 4 points, 4 operators, right? And I put O1, O2, O3, O4 at 4 different points. And I want to know a descendant, well, I just take the derivative with respect to the first point. So I just go to the result and take one derivative of the result. So if you know the physics of the primaries, you are good, because then the descendants are easy, are just derivatives of the primaries. Okay? Good, so now we continue our definition. So in a CFT, if we have some operators which are primaries, and we compute a correlation function, O, a primary at position 1, a primary at position 2, and so on, and there are n of them, say, and we compute it, and suppose I compute this in a space-time which is a local a local rescaling of some reference space-time. So I take some space-time and I do a local dilatation of it. Okay? Is it clear? So I do a local dilatation. And I want to write an equation that tells me how does this relate to what it was before doing the dilatation. So in the original space-time. Okay? And the answer is that in this space-time, the only difference is some simple factor, omega of x1, omega of xn, to the power minus delta 1 minus delta n, where deltas are the dimensions of the various primaries. And I'm not sure about factors of 2 and signs, but we will fix them now. So let's do a simple exercise that allows us to fix what these signs should be. So we'll fix them in a second. So for now, don't trust this sign and the absence of a factor. Maybe there is +2 or maybe -2, I don't know for sure. Okay. So this is, if you want, a definition of a CFT. So CFT is like this. And let's see how this, how this works and what it implies. Okay. Good. Any questions so far? Yes.
So this is the definition of the CFT, which part of this is the definition of CFT, because if I have primary operators, I assume they will be like this, but the existence of just primary operators makes the CFT part.
No, this equality. CFT is a theory where correlation functions in different space-times are related by such simple factor.
But isn't this necessarily true for primary operators?
Well, if you... For primary, you mean if I give you some theory and you have some operator which is not derivative of something, that's what you mean by primary? No, it's not guaranteed at all. No. Okay. Very good. So let me see. So let me think 1 second. So what do I want to do first? So, okay. So let me point out, so this is a general definition. Any space-time, it can be curved, it can be flat, and so on. But sometimes, a particular case of this correlation function is when we do conformal transformations, so-called conformal transformations. Okay? So particular case of this general particular A particular case is when I take some coordinates x mu and change coordinates to some new coordinates x tilde mu, such that dx tilde mu is equal to some omega square of x times dx mu. So suppose I do a change of variables where in my new coordinates, my new metric is a rescaling. Okay? So then what this implies for conformal transformations, okay, is the following. It implies that a consequence of that general relation, so let me write it and then we will check it and see that it works perfectly, is that if I compute correlation functions in flat space, now in flat space, this is equal to omega to the minus delta 1 of x1 times correlation function of O1 of x1 in flat space. Okay. So basically what I'm saying here is that when you do this change of coordinates and you have now the metric up to a Weyl transformation, you can think in two different ways. You can think that either you change the coordinates and you change your points but keep flat space, or keep the points but rather change the metric, and the 2 points of view, it's like passive and active must be the same. So this gives rise to a relation where both right and left hand side are both evaluated in flat space. Okay? So let's just make this explicit because I think that is a very simple example that always makes things more clear. Okay? So let's work out the following example. So an example is inversion. So I take a point x mu and I invert it. So I send it to x mu over x squared, right? So I have some circle, a unit circle or unit sphere, and I do an inversion. So a point here becomes inverted and goes to a point here, right? Under an inversion. Okay, so indeed, if you do this transformation, so you call this x tilde mu, the new metric dx tilde mu, you can easily check. It is just dx mu over x squared. Okay? And therefore, we see that indeed, this is achieved by doing a rescaling of the metric. I can think of a rescaling of the metric where my omega of x is 1 over x squared. Okay. So now, let's see how it is, how everything we said so far is consistent and fits together. So now let's check all the relations we wrote so far on the 2-point function. So the 2-point function tells me that, as we saw several times already, that O of x, O of y is just a power law. Even this result, I'll derive it in 5 minutes, but for now let me take it. And this is what we want to check, that this is a good correlation function in a CFT, so we have RD. So this is in RD, and I have 2 points, x and y, and they decay with a power law. Now, let's see how things work, right? So, so then, if I compute O of x, O of y, of the same points y and x, but in a new metric, which is now 1 over x squared square times dx mu. So it's now conformally flat. It's not RD, but it's RD rescaled. According to what I wrote, according to what we wrote there, this is equal to some factors of omega, which gives me x squared to the power delta times y squared to the power delta, times the correlation function in RD, which is this. Okay? So this predicts what the correlation function in this background is. On the other hand, I can compute the correlation function not on the point x, but on the inverted point. So I can do an inversion and compute this correlation function after doing an inversion, but in flat space. You see, it's like active and passive. In one case, I kept the point, but did a dilatation, a local dilatation. And this, I kept the metric, but I changed the points. What do we get? Well, I just plug this formula, and I plug 1 over, and I do x mu over x squared minus y mu over x squared. I square this, and then I put this to the power delta. And we do some algebra. We just compute this square here. And what we get is exactly x squared to the delta, y squared to the delta, over x minus y to the 2 delta. Okay? If you compute the square, you can easily see that it works perfectly. Which is exactly what we had here. Okay? Kind of checking what I said before. Okay? So in other words, what I want to say is that when you have this inversion, you have two possible points of view. So you start with some point here, and now you transform. So you can either think that what you did was you consider the transformation that takes this point and sends the point to the point inside. That's one option. Okay? And here you kept the same metric RD. Or an equivalent way of thinking, it's the same, it is just your way of thinking, doesn't matter. You kept the points at the same position, but here now you measure distances different. You now use a metric, ds, which is 1 over x squared times the metric in flat space. So you change the way you measure this, which is like you invert the metric rather than the points. Okay? So of course don't do both. If you do both, you do nothing. If you want to do something, you either do one or the other. Okay? So people are often very, very confused with these conformal transformations, and they put tildes in everything, and they put too many tildes. I don't know. Anyway, this is the proper way of doing it. So this already kind of checks that we got the signs right, because the algebra worked out. But there is yet another example that I find very instructive, which is, let's work out what the two-point function of in a CFT of points on the cylinder are. So suppose I start with points on the plane, so I have 2 points here on the plane, and I have this power law decay, and I ask, what's the correlation function when I have 2 points on the cylinder? Because the plane and the cylinder are related by conformal transformation, so if I know one correlation function, I should know the other now. Okay? And this is a very useful exercise that, as you will see, will immediately help us check these signs and make sure that everything is kosher. Okay, very good. So let's try. Right, let's try. So if we start with a metric in flat space, in RD, this is equal to dr squared plus r squared times a d minus 1 sphere. But this is equal to e to the 2 tau times d tau squared plus d squared as d minus 1, where r is equal to e to the tau. Okay? So this is our omega square, right? And what we have here is a relation. We're saying that the metric ds square of flat space is equal to omega square times ds square of the cylinder. Okay? So if I want to know the cylinder from flat space, so here's the relation between the two. And now I can use the formula above, knowing the 2-point function in flat space, to know the 2-point function on the cylinder. Right? Good. So let's do it. So let's see how this works. So I start in flat space, and in flat space, I have a point here in at some coordinate r times some unit vector. And then I have another point here at some coordinate r prime times another unit vector. Now, when I map it to the cylinder, what happens in the cylinder? Now, in the cylinder, I remind you that tau going to minus infinity is the origin, and then I'm doing radial evolution. This is time evolving, right? So there would be here some slice at some tau, which is log of r, and some other slice here at some time tau prime, which is log of r prime, some later tau, right, some bigger circle. And then here there is some unit vector n, and here there is some other vector n prime. Okay? And we are studying the correlation function between a point here and the point here, separated by a distance which is tau prime minus tau. Okay, so what is this correlation function? So now we use the equation above, okay? And we say that the correlation function OO in flat space is equal to omega square times the correlation function in the cylinder. In other words, sorry, not omega square, sorry, omega to the minus delta times omega to the minus delta. Okay? In other words, if I want to compute the cylinder one, if I want to know what's the correlation function, let me use these variables where I have some unit vector and some time tau, and the other operator at some other unit vector and some later time tau prime. And I want to ask this correlation function in the cylinder, it's equal to what? Well, to this omega to the plus delta, because I flip to the other side, and omega is that, so I get e to the delta times tau times e to the delta times tau prime. This is the factors of omega, right? Times the correlation function in flat space, which is, I have some vector n e to the tau minus n prime e to the tau prime square to the power delta. Okay? And now if you compute this square, you just get square of this, which is e to the 2 tau, square of this, which is e to the minus 2 tau, and the cross term. And what you get is therefore that the correlation function OO in the cylinder, so let me spare you some boring algebra, but just write away the result, is 1 over, but even though I'm going to write it, it's important that we check together by head that it looks good. 1 over cosh of tau prime minus tau plus 2 n dot n prime to the power delta. Okay, so let's just see what went on. Even though it's a boring algebra, I want to do, please follow what I'm doing here for a second. So I square this term and I get e to the 2 delta. I square the term and I get e to the 2 delta prime, right? So right now it looks like there is a function that there is e to the tau and e to the tau prime. But when I put this factor inside, I get e to the tau minus tau prime, and the other one e to the tau prime minus tau. And that's this cosh here. But the key thing that you see, because of the signs being plus plus, it works in a way that this thing only depends on the difference between tau and tau prime and not on each individual time. And this has to work. So whenever you don't know the sign, you check time translation in the cylinder, and it's a very good way of figuring it out, the sign, if you did not remember. So apparently I got the sign and factors of 2 right. Okay? So indeed, it's, so as expected, by time translation. It can only depend on the difference. Okay? So you see that a conformal theory is a theory where you can immediately predict a 2-point function on a cylinder knowing the 2-point function on flat space. So it's non-trivial. If you have a massive field theory, if you know the 2-point function on flat space, the 2-point function of the cylinder is a different beast altogether. You have to recompute and rethink about your problem. Not in a CFT. In a CFT, because flat space and cylinder are related by conformal transformation, from one you get the other. By Wild transformation, from one you get the other. Okay, so let's go back one step further, and now that we have some experience with these correlators, let's explore the consequences of conformal symmetry. So I'll do it very briefly, because I've seen that you did it in one of the tutorials that the gang prepared. But I want to do it quickly and understand what should be the correlation function between two scalar primaries, O1 and O2. We know the result. We have been using it many, many times already to check things and so on, but let's derive it quickly. Okay? So what should it be? Well, it should be equal to, if I do a rescaling, so if I consider that I rescale, so sorry, not in RD, but if I do some rescaling, omega square times G, this becomes delta to the minus delta 1 of x, omega to the minus delta 2 of y, times the correlation, the same correlation function, O1 of x, O2 of y, with two scalar operators in the metric G. Okay? Where G, let's take G to be flat space, say. Right? Now, on the other hand, this should be equal, because it is just, because these guys are scalars and this is just a rotation by 180 degrees. It's just flipping who is x and who is y. It should be equal to the same thing with x and y flipped. Okay. Oh. But this can only work if you plug this thing. It should be exactly the same thing with x and y. This can only work if the deltas are the same. So this immediately implies that delta 1 must be equal to delta 2, or otherwise the correlation function O1, O2 equal to 0. Okay? This is a very fast way of proving it. Another way of proving it is just by writing down some explicit conformal transformations and you get to exactly the same conclusion. But I think this is faster. Okay? So now we know they are the same. So we know they have to be the same dimension, right? So we know they have to have the same dimension. So now I can say, let's compute. So now delta 1 equal to delta 2. Okay? And then I can write that O 1 of x, O2 of y, right? Equal. And now notice that if I now rescale by lambda, if I put here lambda x and lambda y, well, according to what we said, it's like for the dilatations, this should be equal to lambda to the minus 2 delta, because this is the same as keeping the metric but doing a dilatation, a global dilatation. So it's lambda to the minus 2 delta times the correlation function at points x and y. Do you agree? Which we define as some function g12 that should depend on the distance between x and y. Okay? And then this thing here is g12 of lambda times the distance between x and y. Right? And now, here, plug lambda equal 1 over the distance between x and y. Right? And you derived in this way that this right-hand side, that the correlation function of x, correlation function of y, equal to some number, because that's just some g evaluated at 1, so some number, let me call it C12, divided by x minus y to the power 2 delta. Okay? Where this is some symmetric matrix. Now, if there is only one primary with some dimension, then we just derive that O with O gives up to a constant 1 over some power law. If there are many primaries with the same dimension, I could get this. But then what I will do in the last step is then what we can say is that we can pick a basis. We can diagonalize this C and pick a basis of primaries such that the correlation function between two primaries, OI, OJ, is just diagonalized, so they become orthogonal, and I can rescale them to absorb this constant C, and then downstairs I get x minus y to the power 2 delta. Okay, and this is the result that a two-point function in a conformal field theory is just a simple power law. Okay? What about three-point functions in a conformal field theory? Okay? So what about three-point functions? Okay? Okay? So, three-point functions, the claim is that they are also fixed by symmetries. So let's see what we could say. So we want to understand what's the correlation function OI of x, OJ of y, OK of z. Okay? So, okay. Sometimes I want to use this notation to write some compact formulas, but I don't know. Okay? And then this guy has dimension delta 1, this one delta 2, and this one delta 3. I might use one notation or the other. Okay. Then I want to claim the following. I want to claim that this should be a constant, and then the space dependence is totally determined to be x1 minus x2 to the power delta 1 plus delta 2 minus delta 3 times two similar factors where you interchange the indices. So x2 minus x3 to the power delta 2 plus delta 3 minus delta 1 times the last factor x3 minus x1 to the power delta 1 minus delta plus delta 3 minus delta 2. Okay? Okay. So, a priori, you would say, well, if you call this R12, okay? So let me tell you what is good about this formula. So what's good about this formula is that you can take this formula and check that this formula transforms as you expect for any conformal transformation. So you take any of the conformal transformations we saw, right? And check that it transforms as it should under any conformal transformation. Okay, so this is a possible three-point function. Now we want to show why is it unique, right? So why is it unique, okay? So one way, so before, let me just point out that Rij square, which I define as xi minus xj square, goes under an inversion, which was something that we implicitly used when we were doing this inversion, becomes xi minus xj square divided by xi square xj square. Okay? And also, I want to point out that special conformal transformations are nothing but inversions, translations conjugated by inversions. So you can think of a special conformal transformation as inverting, translating, and inverting back. That's what a special conformal transformation is. And given that, you see that now if you look at this formula, what do you need to check? Well, rotations, it's obvious, right? It only depends on distances. Translations is obvious. Dilatations, it's obvious. You just dilate all points and check that you get the right power. So the only one you need to check is a special conformal. But special conformal is just checking inversion, because if inversion works, P already checked, so everything works. So we just need to check that under inversion, this formula transforms properly. So you just need to use this transformation rule for inversion. You see that as you transform, you pick powers of x squared upstairs. And you just need to check that you get the appropriate powers to work out as we said. Okay, so it's really, you can do by head. It's 1 second. Okay? So we check that it has the right properties. Okay? Now, what could we have missed? Naively, we could say, well, what about some function here that could be invariant under dilatations? For example, a function of R12 over R23 and say R12 over R13, a function of two variables like this. So indeed, if your theory is scale invariant but not conformal invariant, which is a weaker statement, so if it's only scale invariant, which means that you can rescale but only globally, not locally, this is the general thing that you expect. But in a CFT, this doesn't work. You see that if I rescale, if I do an inversion, this function here is not invariant. I'm changing the slots. Okay? So therefore, this function here is ruled out. It must be 1 by special conformal transformations. But if you have just a scale invariance, indeed you can put this function there. Okay? Now, there is a faster way, an even faster way of deriving that this result is what it is. So I first write it down and say that under inversions it's good, right? Okay. Now, all I actually have to do is tell you that whenever you have 3 points, that you can always map them. So the claim is that if I have 3 points, x1, x2, x3, I can always map them by a conformal transformation to say 0, 1, and infinity. Okay? Why? Because once I map them to 0, 1, and infinity, then I would know that my correlation function would be equal to a bunch of omegas, to some powers, times the correlation function when they are at 0, 1, at infinity, like we did before for 0 and 1, when we rescale and make the separation between them 1. So then I would derive the result, right? So if I know that there is a conformal transformation that maps me here, I just say this is a number, this is what I callCijk, and I just need to work out what this omega dependence gives, right? And because I know, and then whatever it is, and it is unique because I just computed it. But if this works, it must be the solution. Okay? So finally, how do I show that I can put any 3 points at 0, 1, infinity? Okay, let's see. So imagine I have 3 points, and I want to map them to 0, 1, and infinity. So first we can make a translation to put 1 at the origin. Now we do an inversion. That guy's at infinity. Now we do another translation to put another 1 at the origin. So now we have 1 at the origin, 1 at infinity. Now we do a rotation until the third one is in the x-axis. And then we dilate it until it's at 1. Okay? So we can always map it to 0, 1, infinity. Good. So.
Sorry, what special conformal transformation? What does that correspond to? Which Lorentz transformation does that correspond to in R2D?
In R2D, this was this was J plus mu.
What is that?
It's a boost. I mean, it's a combination of, right? This is a light cone direction, remember? So this was a light cone direction, a combination of the first and the last component. And so if you remember, so we have the hyperboloid, right? And there are, so our y's, we decomposed into our x, our embedding coordinate. We said there is a 1, there is an x mu, and there is an x square, right? This is the plus component, this is the minus, and this is the middle, right? So now the Lorentz rotations naturally split into 3 groups. Either you mix the middle index, this is just Lorentz of a small x mu. Or you rotate this guy and this guy, it's also simple, and this is just dilatations. The remaining ones that are a little bit complicated are when you mix this guy with this guy. So you mix these 2 guys, and you get the special conformal. And if you rotate these 2 guys, you get translations. Right? So it's a particular boost of this light rays. Okay, but now, so then what about 4-point functions in a conformal field theory? Well, 4-point functions now, they are no longer fixed by symmetry. So we saw that 2 points and 3 points, they are fixed by what's called the CFT data, which is the set of all, if you give me all dimensions and allCijk, I get immediately the 2 and the 3-point function. So give me the set of numbers, and immediately we know the power law behavior and the coupling between 3 operators. For 4 points, a priori, I could say that now I have my correlation functions of my operators, x1. And a priori, so let me do the particular case where all deltas are the same. Okay? Just because even in this case it's not fixed by symmetry, but it's trivial to do the general case. I could also write something that transforms appropriately. It would be x1 minus x2 to the 2 delta times x3 minus x4 to the 2 delta. So this would transform according to the correct transformations if I take operators with all the same delta, right? It's just a product of 2 2-point functions, each of them transforms accordingly. But now you see clearly I can multiply by any function of cross ratios, because cross ratios are invariant under conformal transformations, which now we see very well, because if I have these ratios of distances, and if all points appear up and down, you see that when you do an inversion, those factors xi squared and xj squared, they just drop, right? So there are 2 cross ratios that I can construct, u and v, where u would be x1 minus x2 square, x3 minus x4 square, divided by x1 minus x3 square, x2 minus x4 square. And v is, I think you flip, is u, where you flip a 1 and 4. No, 2 and 4. Okay. These are the two cross ratios you can make out of 2 points. And of course, you cannot fix this function because it's invariant under all conformal transformations. Why? Because this combination is just invariant under all Lorentz transformations. This is the simplest way of saying it. Remember, this combination is just, if you remember, in the embedding language, this was just capital X1 dot capital X2, and so on, which obviously is invariant under Lorentz transformations and rescalings. But you can also see that it's invariant under conformal transformations in this language because inversion is the only one that you should really check. All other ones are obvious. It's obviously invariant under rotation and dilatations. Okay. So it looks like in a CFT, if you know that what's called the CFT data, you know the 2 and the 3-point functions, and then starting at 4-point functions, there is a new function. Okay? Okay, good. So now, so next, so that's what we are going to do now. So we are going to see that the CFT data is enough. That actually, if you know the CFT data, we can find this function f. Yeah? Well, this is something important and very powerful in a conformal field theory. So in a conformal field theory, if you give me this CFT data, you basically give me everything. That's the claim. So a definition of a conformal field theory, the conformal field theory is this set of numbers. Okay? Okay. What percentage of this was trivial and known to everyone? 100, 80, 90, 15? Did you know most of it, or? Yeah?
I didn't know it doesn't only work for 2D, but for general D.
So for general D, it was good to see this, you say, okay. So I have the option of going on or stopping earlier today and tomorrow exploring 4-point functions. What do you prefer? So yesterday we went a little bit over time, so I'm willing to go under time today, or I can show you why this apparently surprising claim is enough. Who would like to stop? 1, 2, 3, 4. 5. Who would like to continue? 1, 2, 3, 4, 5 also. So, so gang decides. So, no? Let me see if there's something that I can say that doesn't take too much time and that can be a good summary of. No, I'm inclined to stop here. Yeah, I'll stop here. Yeah. Yes.
I thought that when you wrote the coordinate transformation as a particular case of the conformal transformation, I thought that was the definition, but you defined the CFT in different ways. So.
Yeah, I would like to. Yeah, so the question is whether what's more important, if it's conformal transformations or wild transformations. Wild transformation is more general, right? Wild transformation allows me to go from flat space to a cylinder. Or I can do more crazy stuff. I can really take flat space here and now do a wild transformation where I rescale space-time differently in various positions. If you think a little bit, it's kind of insane that we can say what the correlation functions are after doing this crazy thing, right? So we take our space-time and now we say, oh, in this region of space, I'll dilate the space. And then there, I'll dilate by some different thing, and so on. And then, apparently, the net result of this is something very local, where you just care about where do you locally deform. And that's the prediction of That's, if you want, what happens in a CFT.
Is there a CFT that should not be interested in terms of this kind of coordinate transformation? Like that is much more general, but should not be interested with this kind of change of coordinate? Like if I accept that particular.
Yeah. This definition implies these transformation laws when I stick to flat space, right? Yeah. But it also helps me relate cylinders and spheres and stuff like this that otherwise would be harder to understand. But if you're asking for most purposes, is it enough to stick with flat space? Yes. Often it's enough to stick with flat space, yes. I personally like more this thinking of, it's a bit like if you have a magnet and you are studying some critical system and you know that you have no scale, right? But you would like to think that I should have no scale locally, so I should be able to change locally what happens, right? Because I should be able to change locally the scale in this piece of magnet and also in this piece by a different amount, and who could stop me, right? Because being at a critical point means that I can scale and nothing should happen. But why can't I scale a little bit here and more there? And then this is kind of more in line with this picture of local dilatation, so I like it more. But of course, as we saw today, for example, when we were using this power of conformal symmetry to fix 2, 3, and 4-point functions, we were using a flat space, and it was enough.
In this Ising model that you example you mentioned, is the CFT data fixed by the interactions, the microscopic details? And what fixes the CFT data in this example?
So the CFT data, we would, you mean how do we compute it in practice?
Yeah,
Say
you have some magnet which is near critical temperature.
Right.
What determines the CFT data?
It's the 2 and 3-point functions. So if you are an experimentalist, you would measure the critical exponents. You would measure correlation functions and see how they decay with distance, for example. They also imply the behavior of magnetization and susceptibility close to the critical point automatically, so you can also do that, measure that. So critical exponents is the favorite thing of experimentalists, right? You measure critical exponents, how things decay, and so on. That would be how you would measure deltas. To measure the 3-point function, you'd have to do correlation functions now, of like measuring the magnetization at 3 different points and seeing and studying the 3-point function.
Is that determined just by the dimensionality of the system?
No, not at all. It's very non-trivial. These numbers are very non-trivial numbers. For example, take Ising model in 3 dimensions. Ising model in 3 dimensions has a critical point. Ising model in 3 dimensions is a model. It's just a model that spins up and down. So it's just up and down on each side, and they are coupled. And there is a critical point. At that critical point, I can zoom in and zoom out, and my configurations look the same, and I have some critical exponents. Those critical exponents, they are known numerically with like 10 digits or something, but we don't know what they are exactly. It's a strongly coupled field theory. So to study that field theory, we need powerful methods. So tomorrow I'll tell you, for example, how people computed the exponents of the 3D Ising model.
What are the O's in that example?
Sorry?
What are the O's in that example?
The operators that would be most relevant in the Ising model, so there are many operators, right? But the most relevant ones would be the energy density and the local magnetization. So, yeah.
Is there a way, so let's say we start with this definition where you have some general metric on the left-hand side, omega squared, some general metric on the right-hand side. Mm-hmm. Is there a way to then derive that relation, or to get to that relation?
To the first one there?
Yes.
Oh, but what's the difference between that and what you said now?
So, I mean, let's say we take a definition of a CFT to be something where your metric transforms in that way. You have like some metrics, some omega squared, some other metric.
Yes.
You take that as the starting point, and then how can you get to this relation?
I think that one is more general. I think that one is more general. It's like conformal transformations. It's the statement that sometimes you have this possibility of thinking in 2 ways. Right? Sometimes it's a luxury. Sometimes you can say that I don't change space-time, I just change points. But not always, right?
So you're saying that
it's not always true. Okay. That is a more powerful definition. Right? So if I tell you that here, in this room, I will rescale points a bit, but in the rest of the universe, no. It's not obvious that this is the same as just moving the points around. It might not be. I think in this particular example, yes. I can think that either I invert the points or I do a dilatation. Right?
Yeah, because
But the general Wild transformation, which is a local dilatation, is definitely not a change of variables. In fact, the only change of variables that work are the ones we listed already, are the ones corresponding to the 15 conformal transformations. So there are 15 generators, dilatation, translations, rotations, so on. You count, there are 15. There are only 15 change of variables that, for which we have this luxury of thinking that either we do a dilatation or we do a change of variables.
So if we start off with the definition where we say that a conformal field theory is a theory which preserves angles, and just stick to that, and then write down how the metric should transform, which would be something like that. You're saying that
That's right.
the definition of a CFD should be bigger than that. I mean,
No. Your definition, I think, is this one. You are telling me that I should have a theory where only angles matter, so when I rescale the metric, things should not change. But okay, should not change is too strong. Things should be covariant, not invariant, right? Because okay, the operators do have some dimensions. So if I change the field, even in flat space, it's a power law. So when I dilate them, I should pay some factor because of dilatation, but some simple one. So this is like saying invariance. It's saying if you know the physics in some metric, you know the physics in some metric which is just rescaled. So it has same angles, but the different distances. But the angles are the same. And it's invariance of the theory under this transformation, but not invariance, but rather covariance, because operators do carry some scale. So if an operator carries some scale just by dimensional analysis, when I rescale it a bit, the operator must be rescaled by that factor at the position of where it is inserted.
so if I rescale all the x's to x tildes on the left-hand side, then the correlation function should be exactly the same if it's a conformal field theory.
Yes, because you are doing twice the work, so you are undoing what you did. So then you are doing nothing. If you say that there, I take a point and make it inverted, and I also change the metric, but then you are not doing anything.
So, but then in that sense, it will be if you can say that the correlation functions are invariant and conformal functions. Or you're saying that that's
No, that second thing of doing it twice is doing nothing. No, that's nothing. That's not doing a transformation. That's just saying that one coin is equal to another number in another coin. I mean, it's nothing. It's just.
But then if you say that there's some symmetry in the theory, doesn't that imply that your correlation function should be invariant under that transformation? Are you saying it should be just covariant?
No, it's covariant. It's like if you have a theory with O3 symmetry, it means that your vectors should transform as vectors. I mean, but they still transform. So, I mean, yeah, invariant in physics means covariant, means that, I mean, yeah, there's not a big difference. Yes?
We've got the 2 and 3 point functions in flat space now, and we can transport them to any other space that's related by wire transformations.
Exactly, yeah.
But not any space, right? Because
not any space.
whatever we can access to these Y transformations is still conformally flat.
Absolutely.
Okay.
Absolutely. So right now, what we showed was that in flat space, we can fix the form of 2 and 3 point functions. And tomorrow, I'll show you that we can also fix the form of 4 point functions. So we can fix the form of correlation functions in flat space. And then there is this nice thing that in a conformal theory, we know what happens in a different spacetime. You see that in general, it's a very beautiful question if you have a physical system where you measure in the lab that there is no scale, because typically that's what's easy to measure in the lab. You zoom in and zoom out and see that things don't change. But then you ask, is it scale invariant or is it conformal invariant, which is stronger, right? And it's very non-trivial. So people, for example, they simulate the Ising model on flat space, and then they simulate it on a sphere and study correlation functions in both. And if the theory is really conformal, these two things should be related to each other. It should not be independent. We should find, and indeed, there are many, many checks of real conformality of the Ising model. Actually, they were, for example, this check of the sphere was done last year or 2 years ago or something like that, for example, using Monte Carlo method, simulating the Ising model on the sphere, and really checking that indeed, the map between the sphere and the plane is what we would expect. Yeah.
So you're saying we can access these correlation functions on any space, or is there some restriction?
No, we can study it in any space, but it's not like all spaces are related in a trivial way, right? If your space differs from mine by local dilatations, then the physics are such that the theory doesn't care about local dilatations in the sense that I described now, that we can find what it is. If you give me now another space-time that has, say, different topology, like a torus or something totally different and so on, and there is physically no reason why I should be able to tell you what it is, and indeed there is not. A black hole is not just a local dilatation of flat space. it's fine. I don't know indeed how to compute correlation functions in a black hole directly from knowing this one. That's normal.
So then this results with the conformal data stuff. That's only true for spaces which are related to flat space, which are conformally flat.
The fact that if you know the CFT data, you know everything?
Yeah.
I think this question you should ask me after I explain why this is enough. Otherwise, it's kind of, the answer is no, but it's not very illuminating because you have no idea why this is true to start with. So. More questions? So let me just tell you something. So do the following exercise of, remember that you studied this problem of doing this 3-point function. And what you did find was indeed that the outcome was this. Now we see it's not a miracle. It had to work because ADS had these isometries. These isometries are conformal transformations and they imply this form. Right? So it had to work. But that is an example where you did compute some CFT data. You had some masses as input, some M1, M2, and M3, which were related, I remind you, they were exactly the same as delta 1, delta 2, and delta 3. So this was part of the CFT data. It's some input. I give you some dimensions. But then you computed these structure constants, C1, 2, 3, by studying these geodesics, interacting, and so on. So I'll ask you to look at your result and tell me what happens when these masses are very large and all equal. All equal is enough. Okay? So go back to the homework and tell me what is this 3-point function in the limit of very large masses, and think why the physics is such that it looks reasonable. Okay? And tomorrow I will tell what the answer is and use it a little bit. Okay, see you.